What's up everybody, I'm Jason, and in this video I'm going to talk about how I figure out how powerful of a light, how much light I need to, for example, when I'm buying or renting a light for a video setup or to shoot something or to just equip myself with better lights. So before I get into the actual process, I need to at least touch on a note on the math. There is math involved in this. And specifically, there's one operation involved in this that may or may not be directly possible on your calculator that you would be using for this, and that is a binary log, or a log in the base of 2. Now, fortunately, there's good news and there's a way to deal with this. So first of all, if you're using an iOS, an Apple iPhone as your calculator, I have great news for you. Apple decided that this was a function that should be built into the calculator. And so all you have to do is turn your iPhone on its side, so it's landscape, and it switches into the scientific calculator mode. So this is the native Apple iPhone calculator app. And then you tap the second button, which is in the second row all the way to the left. And then you will see just to the left of the 4 is a button that says log with a little subscript 2 next to it. That's the binary log function, and that's all you need to do for the binary logs in this video that are going to be done in this video. Now, unfortunately, if you're using an Android phone or even something as kind of massively overkill as a TI graphing calculator or a general scientific calculator, what you'll find is that they won't have generally, at least I looked on some Android phones and Googled a bit and couldn't find a binary log function in the built-in calculator app. Now, obviously, third-party calculator apps may in fact have it, but for a scientific calculator or Android phones, they generally, in my experience, don't have a binary log function. What they will have is either a log, which just says log, and it's in base 10, or a natural log, which just says ln. And so you have to do a little bit, one extra step when you're doing, to get to a binary log with these calculators, and that is you have to divide. You can use either the log base 10 or the natural log, and then for the calculation, so you would do the calculation using one of those two, as you would if you were doing a binary log. However, you then divide the results of that calculation by the same type of log of 2. So, for example, if you're using log base 10, you would do the log base 10 of the calculation, and you divide that by the log base 10 of 2, and that will give you the same output. Now, if you're super adverse to doing any kind of math whatsoever, I have written a tool that does all the calculations that I'm going to do in this video. You can go to my website. I will put a link in the description below, and you can fill in the information that the tool you need that you need to do this. So your aperture, shutter speed, your ISO, your subject to light distance, and the amount of attenuation that's lost, or the amount of light that's lost in the diffusion of your light modifier. And all you have to do is plug that in, and it will come back and tell you the results. However, I'm not going to walk through that in this video. I'm going to walk through doing the process manually so that you understand where everything's coming from and what everything's doing. And then, obviously, you can just plug in numbers. So perhaps unsurprisingly, this whole process starts behind the camera with how you want to shoot things. So if you imagine the way light works, you have light shining on a subject, the light illuminates the subject to a certain level, the camera bounces off the subject, the lens collects it, focuses on the sensor, and then you look at the picture behind the screen and go, yep, that's a good picture. That's exactly what I wanted. Well, this whole process kind of does the reverse of that. So you have to start with how you want to shoot things. So this means you need to know your aperture, or the aperture that you want to work at. So, are you a depth of field junkie that wants to shoot at f1, or are you somebody who, you need to have a reasonable amount of depth of field, so you're shooting at f8 or f16 or something like that. You need to know your target frame rate. Well, technically what you need to know is the shutter speed, However, if you're shooting video, shutter speed and frame rate are sort of intrinsically linked. So you need to know the frame rate you want to work at and therefore the shutter speed that you're going to be shooting at. So for example, if you're shooting at 24 frames per second on a hybrid camera, you'd be shooting at a shutter speed typically of a 50th of a second. If you're shooting at 120 frames per second, then you would be shooting at a shutter speed of a 2/50th of a second. Additionally, I should point out this all applies to still photography too, where you just don't have to worry about the frame rate. But if you want to shoot with continuous lights, all of this is the same thing. This math is completely, or this process is completely irrelevant of how you're actually shooting. Finally, you need to know the ISO you want to shoot at. So as a point of reference, most cinema cameras shoot at ISO 800. And incidentally, I shoot most of the time on my DSLRs and mirrorlesses at ISO 800, largely because I have found that in my environment, working at ISO 800 is a comfortable light, for my settings, it's a comfortable light level to work at. I'm not blasted with so much light, sucking down so much power that it's heating up the room and it's, uncomfortable to, or difficult to be able to say, look at a teleprompter or something to that effect. So throughout this video, I'm going to work through an example of how I would calculate things or how I calculate things. And for that example, I'm going to be using the following assumptions. So, and this is based on how I typically shoot. So for example, this video, like most of my videos, is shot at 24 frames a second, which means I'm shooting with a shutter speed of 1/50th of a second on a mirrorless camera, a hybrid mirrorless camera. I'm shooting with a full frame camera. I tend to like a little bit of depth of field, but maybe not so much depth of field that it's, massive. I'm not going for either extreme. I'd like a slightly blurred out background. At the same time, I would like to have me be in focus. So I tend to shoot at around f4. And as I said, I tend to shoot at around ISO 800 because for a 50th at f4, that tends to produce a reasonable light level for me to work in. So to start out this process, we need to convert our exposure settings that we're going to be shooting at into a subject illuminance level, because that's basically how we're going to work with this. And this is by far the hardest math step in the process. It's also the step that uses the binary logarithm. And this is sort of a two-step process. The first part of this process is to convert our exposure settings, so aperture, shutter speed, and ISO, into a ISO-adjusted exposure value. So to do this, we use the equation that's on screen now, the binary log of the aperture squared divided by the shutter speed in seconds minus the binary log of the ISO speed divided by 100. So the aperture here, given by n in the equation, is just the f number that you're shooting at, so 2.848, whatever, that kind of thing. The shutter speed has to be the value in seconds. So, I'm using a 50th of a second, which actually converts out to be, in decimal, I should say, which actually converts out to be 0.02 seconds. Of course, the ISO speed is the ISO you're shooting at, say 800, etc. For my example, if I start plugging if I plug the stuff in, the binary log of the aperture squared divided by the shutter speed is 9.64 and a whole bunch of decimal points, and the binary log of 800 divided by 100 is 3, and you do the subtraction, and you get 6.64 for the ISO-adjusted exposure value. The next part of this process is to convert that ISO-adjusted exposure value into a illuminance level in lux. And this is actually pretty simple. All we do is 2 raised to the power of the exposure value that we just calculated multiplied by 2.5. So again, using my example, 2 raised to the 6.64 times 2.5 is 2.49 and a whole bunch of decimal points, which we can round to 250. And so essentially, for me to shoot at a 50th of a second at f4 at ISO 800, I have to be lit to approximately, plus or minus a couple of lux, 250 lux. So the next step of the process is to make this into something that we can actually use for talking about or looking at lighting data from manufacturers, so published photometric data. So right now we have how bright I need to be. What we need to know is how much power a light has to put out at some normalized distance in a photometric number to get that brightness at the distance that I'm actually going to be, or I would actually be from the light. Now, I'm using lux for all of this, and I recommend doing this whole process in meters, in metric. And the reason for that is quite simple, actually. Virtually every manufacturer that provides photometric information for their lights provides it for a 1 meter test difference. If you're doing it in feet, which is where I started when I first started trying to figure this out, the numbers are all over the place. There is no, as far as I can see, standard test different distance. It's some are 3 feet, some are 28 inches, some are 4 feet, some are 6 feet. It's all over the place. And the idea here is I want to do, as much as I'm not averse to doing math, I want to do the math once, and then I want to look at as many different sources that I can without ever having to recalculate the math. So what you need to do before you can start this, we have to sort of go back to thinking about what's going on before we shoot. You have to have an idea of where your light is going to be placed relative to the subject. If you could measure that, great. Like if you're setting up a studio and you know where the subject's going to be cued, and you know where your camera's going to be, and you know where your lights are going to be, that's sort of the perfect scenario. If you don't know exactly where things are going to be, guess. It doesn't have to be, again, millimeter accurate. This isn't rocket surgery. This is an estimate that we are looking at to sort of set the tone. And I build a lot of padding in at the end of this because, well, I'll explain that when we get to the end of this process. So once you know where your light is, we're just going to be dealing with the fact that light drops off following the inverse square law. And so for a normalized 1 meter lighting photometric distance thing, or normalized 1 meter illuminance level, whatever you want to call it, all we do is take the distance that we've measured or guessed at subject to light distance and multiply that by, square that and multiply that by the number of, the lux number that we got in the previous step. Now, technically, this should be the subject to light distance divided by the target reference distance, and that whole thing squared. However, because we're normalizing to 1 meter, the reference distance is 1 meter. Dividing anything by 1 is itself, and we can just simplify the math. So plugging in the example numbers again, if my light is 1.5 meters away from me, I would take 1.5, I would square that, and I would multiply that by the 250 value that I got in the previous step, and I come up with 562, and again, a whole bunch of decimal places, lux for a normalized 1 meter photometric output. So we're going to just round that to 560 lux because it's a nice round number. So basically what this is saying is that if I have to be lit to 250 lux and I need a light that is 1.5 meters away, to light me to 250 lux, the photometric data for that light at 1 meter has to be capable of putting out 562 lux. Okay, now that we know how much light the light basically has to, the light has to put out at a normalized distance so we can look at all sorts of different manufacturers' informations, we have to take into account light modifiers. So if you're shooting with an unmodified LED panel, so you're just straight up LED panel, you're not using any diffusion, softbox, you're not bouncing it off something, and nothing like that, it's just straight LED panel. Or a straight hard light from a monolight style fixture like an Aperture LS120 or so forth, then you can skip this step. The published photometrics for your light will be for the light, and you're just using the light, and you don't need to worry about anything else. However, if you're using a softbox, or, well, primarily a softbox, a a light, something like a light dome 2, or any kind of, essentially any kind of softbox, you have to take into account how much light is lost in the diffusion and the baffles of that light, or that light modifier. And unfortunately, this is not a process that has some easy, simple formula. In fact, ideally, what you would be able to do is look up the light loss from the modifier manufacturer and just plug that in and go with it. However, most light modifiers manufacturers don't even provide that information. There is one notable exception to this, and that is FJ Westcott. They publish in the specifications for their softboxes the baffle and diffusion densities. They're both usually about 1 stop, but you can go look at the specs if you're using an FJ Westcott softbox and know what your light loss is going to be, and you just work from there. Now, if you already have a softbox and you're trying to figure out what that is, obviously the best thing you could do is measure it, if you could figure out a good way to do that. However, you can also estimate it by looking at diffusion cloth loss levels from companies like Roscoe and Lee. So just to put some numbers here, looking at Lee, if you're using a quarter grid cloth, so a fairly light diffusion material, you can expect to lose about 3/4 to 1 stop of light. And if you're using a full grid cloth, which is obviously a substantially heavier diffusion material, you can expect to lose 2.5 to 2 3/4 stops of light. So my rule of thumb is if I can find a number, I use a number. If I can't find a number and it seems like it's a reasonably well-built softbox, I'll just figure on 2 stops. And if I can't, if that's not right, well, I do have, obviously, like I said, padding built in at the end of this process. So to convert, or to address our light levels, this is just a basic stops to linear conversion plus multiplier. So all we do is 2 to the power of the number of stops that we're losing from our light modifier, and multiply that by the normalized 1 meter illuminance level that we just calculated in the previous step. So again, for example, if I'm working with a 4-stop loss light modifier, I take my 560 lux that I calculated in the last step and I multiply that by 2 to the 4th power, or 16, and I get about 2240 lux, or 2240 lux as a... That's what the 1 meter photometric level illuminance needs to be for that light to light me to 250 lux at the distance I'm using it through that light modifier. So once we've done all that, we're done, right? I mean, we've got a number, we can just go out and find a light that does that, and we're good to go. Well, 2 things to that is, well, not so much really, and for 2 reasons basically. First of all, as I've been saying, I want buffer. I want to build in some extra power into my light because, well, the reality is you can usually dim a light, or you can always dim a light, but you can't turn one up to 200%. So if you buy a light that lights you just to the levels that you actually need and not anymore, and then it turns out that you have to move the light, or you have to shoot it at a smaller aperture, or you're shooting at a higher frame rate, or the estimate that you had for your diffusion loss was too low, well, you can't turn the light up, and you would want to be able to turn the light up. So I tend to want to work at less than full power. Additionally, since I'm usually buying lights for myself and for my own use, I want to be able to use them in as many situations as possible. And while in a dark studio, I have complete control over the light. If I'm taking the lights on location and I need to light something and I can't control the ambient light, I need to be able to work with it or overpower it, or at least match it. So I want to work below full power in general. I don't want to be buying a light to use it at full power. However, on the flip side, having a light that's too massively or so massively overspec'd that you're trying to run it at like 1%, becomes a problem too. And the reason for this has to do with the way, and I'm speaking mostly for LED lights here, for older technologies. So in the case of HMI, you only have about a 50% dimming range, so you almost have to be spot on. And for tungsten lights, while the dimming range is a lot wider, when you dim a tungsten light, the filament is heated to a lower temperature, and so not only does it put out less light, but it also puts out, there's a color shift, a color temperature shift. So anyway, back to talking about LED lights. Most LED lights on the market now, at least for video, are built to use a 0 to 100% dimming range, at least the good ones. The not so good ones use less than 100% range, but it's almost always done in percentages. And it's almost always done as a linear control, meaning 1% is actually 1% of the brightness. It's not just some arbitrary step. So what this means is twofold. First of all, a 100% range or 100 value range only gives you about 6 2/3 stops worth of adjustment to be made. So, you know, we're not talking about 10 stops here. So if you're buying a light and you're working 2 or 3 stops below full power, you only have 2 or 3 stops roughly below that to be able to dim it to. The real problem is, and that's not a bad range, it's better than almost anything that had, you know, in video lighting previously. The real problem is because of the linear controls. So what this means is, if you remember, stops are powers of 2, they're halvings or doublings. So -1 stop of brightness would correspond to a value of 50% on the lights control. -2 stops from full power would be, you're down to 25%. -3 stops and you're down to 12.5%. And as you hopefully can see, as you increase or as you dim the light below full output, you're essentially having less and less steps between each stop of adjustment, and therefore you lose a lot of finesse at the very end of the very low end of the power spectrum to control the lights. So you may end up in a situation with a massively overspec'd light where the, you know, if you're having to work at 1%, you know, clicking it up to 2% is too much light, and clicking it down to 0% and the light's off. Now, one good note about this is that some manufacturers, they still sell lights that are 0 to 100% dimming, but they actually don't do the dimming in a linear fashion. And the one manufacturer that I'm aware of that does this is Aperture. I was very impressed or surprised to find, for example, that my LS120D2 actually had a 10-stop range. I used a light meter to check this. Had a 10-stop control range, and that for the vast majority of the steps or, you know, of that range, a stop used about 10%. Some were 9, some were a little bit more, but about 10% or 10 percentage points to cover a stop. There were some exceptions. The brightest stop was more and the darkest stop was less, but generally it was 10% per stop across the brightness range, which gives both a lot of control and a lot of finesse. And of course, their newer lights, the 300D and the 600 Pro, actually have logarithmic curves in them. Now, I haven't tested any of those lights, and I'm not exactly sure the way things, you know, how they work, but a logarithmic curve should give you that kind of, you have stops and you have control through the range. But again, that's something I haven't personally tested. Now, of course, one solution that you always have, as I said, you can always dim a light that's too bright, and you can do that using this, neutral density. This is, you put it in front of the light, you can knock off 1, 2, 3. I think generally it kind of only goes up 3 stops or something. You don't want to use too much neutral density if you can avoid it, because all you're doing is running a light that's producing a lot of light and a lot of heat into a piece of neutral density that's blocking a lot of the light, and so it gets hot. But it is a way to bring down a slightly overspec'd or even kind of massively overspec'd light into a range where you can control it with the light's electronic dimming. So that's pretty much it, just a little bit of math, and you can narrow down your light choices based on an actual estimate of what you'll actually need, and not just wild guessing, or worse, buying things, finding out it's not quite right, and having to return it. So if you found this useful, please consider smashing that thumbs up button, and if you like this kind of thing, you know, more technical discussions on how to do things with photography and videography, please consider subscribing. As always, thanks for watching, and I will see you next time.